Hello everyone, I hope you hear me well. My name is Petro and I'm glad to present you our conference paper, which is the hidden pitfalls in deep learning-based identification of medical tools. This paper was made with cooperation with IT department of the First Medical Union of Lviv and Ivan Franko National University of Lviv. Let me proceed. So, efficient and accurate recognition of medical tools is essential in clinical environments, particularly for supporting surgical workflows, inventory management, and automated documentation. In the context of the ongoing aggressive war against Ukraine, the needs of the national healthcare system have intensified dramatically. Hospitals and field surgical units face serious shortages of qualified personnel and equipment, while the volume and urgency of surgical operation continue to rise. Given the limited availability of specialized tools, especially in high-demand environments, the need for rapid automated quality control is paramount. Recent advances in deep learning, particularly only look-once family object detection models, have demonstrated strong potential for real-time medical image analysis and surgical tool recognition. A persistent and serious problem in surgical practice is the absence, breakage, or loss of instruments in operating suites. Clinical teams frequently encounter situations where a surgical kit is opened only to discover a missing instrument, a damaged component, or an inappropriate substitute from another kit, which can compromise patient safety and delay the procedure. Also, the extreme diversity of surgical instruments exceeding more than 10,000 unique types currently used in hospitals makes comprehensive manual annotation infeasible. To address this challenge, we formulated and verified a scalability hypothesis. If a limited subset of representation instrument classes, 3 in this study, can be reliably recognized using a reproducible deep learning pipeline, the same methodology can be extended to thousands of classes via synthetic data generation. To test this hypothesis, a small dataset of real surgical instrument images was manually annotated with expert assistance and then expanded using synthetic augmentation techniques to simulate diverse lighting angles, occlusions, and spatial configurations. The experiments validated the feasibility of synthetic-driven dataset expansion as a practical and resource-efficient alternative to exhaustive manual labeling. The methodology relied on several key tools and libraries. YOLO V8 provided the core detection model. Docker and Docker Compose ensured reproducibility and portability. Label IMG supported expert-guided manual annotation. Albuminations was used for advanced data augmentation and synthetic data generation. This integrated configuration establishes a reproducible modular pipeline for end-to-end training and deployment. As I already said, every project has its own limitations, and this is not the exclusions. So first, the current model was trained on a limited dataset representing only 3 instrument classes. While augmentation improved diversity, the dataset may not fully capture variations in instrument types, lighting, or occlusion. Second, the current evaluation focused on tabletop scenarios under controlled conditions. Testing in dynamic clinical environments is currently ongoing. Although the Docker-based workflow ensures reproducibility, performance depends on GPU capacity, which may affect real-time inference or lower-end systems. Finally, the current solution still relies on manual annotation and remains labor-intensive. Future work will explore semi-automatic labeling and active learning to accelerate dataset expansion. Addressing these limitations will require collecting larger and more diverse datasets, testing in realistic clinical environments, and optimizing the deployment pipeline to ensure reliable performance across different hardware and operational scenarios. As I already said, for deploying the YOLO 8 model, a Docker-based project was chosen for its universability, reproducibility, and clean dependency management. Separate services in Docker Compose make it easy to scale inference and isolate the environment from the developer system. The first service, label IMG, manage an image annotation and XML file generation, providing a clean and structured dataset for model training. The second service, augmentation, applies various data transformations, such as blurring and rotation, to increase dataset variability and improve model generalization. The third service, training detection, handles the training of the YOLO 8 model as well as inference on new images, enabling efficient and isolated execution of the deep learning pipeline. This modular design allows each component to be developed, tested, and scaled independently while maintaining a consistent environment across different systems. For initial validation, a small image pack was prepared containing 3 main classes of medical instrument under different angles. Since the total variety of surgical tools exceeds more than 10,000 distinct items, a synthetic data generator based on illumination and procedural rendering was employed to simulate new combination of angles, lighting, and occlusions. The model achieved strong validation metrics. As you can see, the training losses, box loss, classification CLS loss, and DFL loss, it means distributional focal loss, consistently decrease, showing a smooth downward trend. Box loss, which quantifies regression errors for bounding box localization, starts above 3.0 and converges below 0.5. Similarly, classification loss begins near 4.0 and declines toward 0. The trends indicate effective learning and reduced prediction errors. Validation losses follow a comparable pattern, albeit with slight fluctuations due to batch variance, suggesting consistent generalization. Precision and recall steadily increase over epochs, initially fluctuating but stabilizing around 0.9, 1.0 towards the training conclusion. Mean average precision shows repeat growth, plotting near 1.0, which confirms the model high detection capabilities. F1 precision recall versus confidence curve suggests an optimal confidence threshold around 0.5, 0.6. F1 is near 0.99, near 0.51. The confusion matrix for the evaluated split is essentially diagonal, with no cross-class errors, indicating consistent labeling across classes 100, 101, and 102. In figure, you can see a confusion matrix illustrating the classification results for 3 classes. All classes, as is shown on the table and a figure, were correctly identified with sufficiently high confidence scores. However, this evaluation was performed on a small baseline augmented dataset. To obtain more ecologically valid performance estimates, the model should be tested under more realistic conditions using a larger and more diverse set of real images. Overall, this study demonstrates the feasibility of using YOLO V8 for tabletop medical instrument recognition, providing a foundation for future work on larger, more diverse datasets and deployment in realistic clinical environments. A key contribution of this work lies in the harmonization of all stages of the deep learning pipeline, from expert-driven annotation and data augmentation to training and deployment. The developed YOLO V8-based recognition system can be integrated into hospital information systems for real-time surgical instrument verification and disinfection control, potentially reducing preparation time by 20–30% and minimizing the risk of missing or misplaced tools. The approach thus supports surgical workflow optimization, inventory management, and patient safety, aligning technological innovation with the humanitarian need to strengthen Ukrainian medical infrastructure under wartime constraints. Future research will expand dataset diversity to include more instrument types, orientations, and lighting conditions, enabling ecologically valid testing and stronger generalization. For me, that's all for now. Thank you for your attention.